everyone. You are very welcome here. The talk today will focus on EDR evasion as well as some Windows internals. So the talk is named EDR versus bad guy, the never-ending story. Why it's a never-ending story? This is what we will try to explain during this presentation. First of all, we will do a short introduction. Who am I? My name on social network is KMKZ Security. I'm 42. Quite old, I know. I worked previously as a penetration tester in France and after in Luxembourg in several parts. I worked on inside several companies and as a red teamer and penetration tester. And now I'm working as a manager for Cyberforce Offensive Security, which is COS. This is the thing we can see on the t-shirt. I know that everyone has the reference about this, right? So, yeah. And I released a lot of papers, CVs, etc., etc. And now my goal is to share my experience and my knowledge with my teammates to help our team to grow using the offensive mindset.
Yeah. So I'll present myself. So, hi guys, I'm Anthony, Maestre. From Twitter, it's YOLOPOM. I'm a pen tester and red teamer since 2017 in the Jean-Marie team. And during our mission, like doing adversary simulation, some stuff, and assume breach, I had to focus myself on EDR bypass. So that's what the talk will be about today. I have some CVEs. I'm the author of the postdom tool. And then it's the first time I'm diving into kernel land, so be kind.
But not the last.
Not the last. Yeah.
So why this talk and the short overview about the agenda? As Anthony said, we are performing a lot of realistic offensive tasks such as adversary simulation or red teaming activities. Doing this kind of activities, you have no other option than developing your own tools because you have the same constraints threat actor will have. And you also have one more, which is the attack scenarios, the objectives, so it's 2. And the last one, but very important, it's time limited. So the goal here is to have several R&D projects. We will present postdump, and postdump is maintained and developed by Anto since 1 year, something like that. And why this project? It's because EDR solution is a hot topic right now, and this project is quite well advanced, so why not? It will present some userland and kernelland stuff. It will not go in details on some techniques because they are already documented somewhere else, and we prefer to focus on the kernel part, which is focused during research and development. But we wanted to keep it in the slide deck because we know that the slide will be shared later, and in case someone wants to explore and have some question, it's possible to contact Anto and asking him. As a kind of bonus, he will also show how to abuse arbitrary read-write in kernelland, of course, for LPE. So it stands for local privilege escalation. And at the end, you will have conclusion and a question, but I guess question will be done during lunchtime because it's quite challenging for us. Just one last point, and after I will let Anto present his topic. Now, as I said, I'm his manager, and I encourage people to share their knowledge. I guess it's also part of the job for offensive security guy to become a manager and to help people to grow, develop their skills, and to share with other guys, because this is how a community should work, and this is how we can share the knowledge and develop this community. So now the manager will go behind and Anto will present his topic. So make us read.
So let's start. So about EDR, XDR, telemetry sources, we have the mini filters, the binary process scanning, sandboxing, but we will not talk about this because unfortunately we don't have the time. Only 34 minutes remaining and we have a lot of stuff to see. So I prefer at least show to everyone what kind of different techniques exist, just for you to be aware about them, and then maybe deep in more details into the kernel land. So we will mostly talk about the AMSI, the ETW, the hooking, the ETWTI, and the kernel callbacks. So as you can see, there is the, let's say it's divided in two parts, the user land and the kernel land. Inside the user land, we have the MSI, the ETW, and the hooking. And inside the kernel land, we have what we call the ETW-TI, the kernel callback, but also we'll see some process tampering techniques. So first of all, the MSI. The MSI is the Microsoft component for anti-malware scanning interface. Basically, it works mostly with scripting languages like PowerShell, Windows Script Host, JavaScript, VBScript, and the Office macros. It supports also .NET for the assembly load function. What is important to know is that some EDR supports MSI, some don't. Even if now, I guess, it's most EDR support it, but still good to know and to check if you want to buy some EDR solution. The MSI is mainly working using two functions, which are the MSI scan buffer and the MSI scan string. So, for example, we can see here that just loading a known binary, which is the sharp-up. So we use in the .NET framework the assembly load function. At the moment where the executable is executed, for the assembly load function, the MSI DLL will be loaded into my process, and then the byte buffer will be scanned by the MSI scan buffer function. And you can see that, it's in French, sorry, but you can see that the system just returned the message that the virus has been found inside the binary, which is the sharp-up, simply. So how can we patch this? If we look at the MSI function, the MSI scan buffer, we can see that there is several checks, and these checks are all returning to the same location, where we can see we have the instruction which is move inside the EAX register a specific code. If you just look at the Microsoft documentation concerning this code, we can see that it's about the invalid argument. So what we can simply do is create a code to simply rewrite the first instruction of the MSI scan buffer, moving inside the register the invalid argument code, and just return. And as a result, then what we have is that we're just patching the MSI, we load the same assembly that we loaded before, and just bypass the MSI scanning. Then we have the ETW. So ETW is the event tracing for Windows. It logs pretty much everything. As you can see here, we can use Logman to see every providers. So it works with providers and consumers mechanism. So the providers is simply the system, and the consumers are, for example, the EDR solutions that will request, that will register to some providers to have specific logs. And it uses the NTDLL ETW event write and the NT-trace event to write logs. So what it means that it's inside the user land. And if it's inside the user land, it means that we can simply just bypass it. So at the right, we have the assembly of the ETW event write function. So for example, let's just subscribe to the .NET runtime provider with my .NET assembly. What you can see, for example, if I execute my tool and register to the .NET provider for the ETW, we can see that we have some logs. So we see the command line parameters, my function names, the namespace name, and the class name. So we can just proceed as we did for the MSI, just patching the first instruction of the ETW event write, just with XOR of the register. And as a result, you don't see nothing anymore. So meaning that no logs are not write anymore inside by the ETW function. So the system and then the EDR also just see nothing anymore. Then you have the hooking, let's say the most important part. The hooking works with the kernel callbacks, but we will see this just after and more in details. So the hooking by the EDR are mainly, the role of the hooking is to redirect the traffic of the execution, to redirect them to the module of the EDR. So for example, here on the left, we have the not hooked function of the NT-read virtual memory. And then on the right, we have two different EDR. We can see that the hooks are different. So it really depends of the EDR solution. So let's take an example of we take the NT-write virtual memory function. We will call the malware, let's say, we'll call the NT-write. So the EDR will redirect to his own modules, which will allow him to analyze the arguments that are passed to the NT-write virtual memory function. So let's say, for example, the buffer size, the buffer content. So the EDR will analyze the size and the content of the buffer that the malware wants to write, and will decide if it's something malicious or not, if you have to block it or not. So let's say the hooking is very important to bypass for a threat actor. So we have different solutions. The first one is simply the unhooking. So for this, we have to load the NTDLL from the disk. At least we have to find a way, can be whatever way, there is different solution, like allowsgate, for example, which consists of taking the unhooked function based on the neighbor. But what we have to know is that the EDR is hooking the NTDLL library or also the kernel 32 library, which are mapped inside the process. So the goal is to load another version of the NTDLL library. For example, we take the one which is on the disk. We will grab the unhooked function and just rewrite inside our current process the unhooked function. So you can say I did a tool just to proceed doing this kind of stuff. So in my case, I'm doing the unhooking using the tinvoke that we will see just after. But I grab the unhooked version of the function, just rewrite it. And if you look at inside the real NTDLL function, which is mapped inside my process, the function is now unhooked. But the bad point of this is that it can be spotted by the EDR if the EDR is periodically just checking if the hook is still in place or not. Another technique is the tinvoke. Like I said before, we're just grabbing the NTDLL, which is on the disk, inside the C Windows 32 folder. And we allocate some space inside our process to map the DLL manually, and then simply calling the function inside the new mapped NTDL space inside our process. So here then we have two different allocations. So we have the real NTDLL inside my process, which is mapped at the process creation, which is hooked. And then we have the NTDLL version from the one I took on the disk, which is unhooked. So we are just calling the function directly there. The EDR can spot this kind of stuff using the load image kernel callback. You will see that simply the NTDLL, which is on the disk, is loaded inside the process, which can be kind of suspicious. Then we have the EDR trampoline. Quite unstable, cannot work with every EDR. But basically, we can see that the EDR is rewriting the prologue of the function and the syscall ID. But then they must be stored somewhere because the EDR, once the hook is performed, you have to redirect our, let's say, our call to the legitimate function. He has to still execute our function. So we can suppose that the EDR is storing the bytes somewhere in memory. So here we are just doing a scan of the memory to find the byte of the function. And then once we found it, for example, we can see that we found the pattern of the byte we were looking for the NT-read virtual memory. We saw that we found it. So this is inside the EDR module. And we can see that the EDR is doing a jump, which is located inside the NT-read virtual memory plus 0x8, which is simply redirect at the test instruction just after the hook. So basically, we can directly call our function from the EDR stored byte to bypass the hook. We have to go fast, 24 minutes. So then you have the direct syscall. So basically, the direct syscall consists of just rewriting the complete function instruction inside the memory of the process. So we can just allocate some memory space to write the syscall, or just trying to found already existing read-write executable memory space inside our own process and use it to write the syscall and execute it. Then we have the indirect syscall. So compared to the direct syscall, you can see in the previous slide, in blue, we are rewriting the stub, the syscall ID, the int syscall, and the ret. But for the indirect syscall, we are just rewriting the stub, the syscall ID, and then we are doing a jump. So basically, we can see that the EGR never hooked the syscall instruction. So our goal it will be to jump directly in the legitimate syscall instruction of the NTDLL library. And it's always located 18 bytes after the first function instruction. So basically, we will get the address of the function. We will add to it 0x12, which will be the syscall instruction, and then jump on it. So it will appear more legitimate for the EGR because, as you can see, we just write on the top. So on the top, what you can see, the instruction, the bytecode, we write ourselves inside our process memory. And then we write the jump inside the R11 register. So basically, we will call the function here, and we will jump directly at the syscall instruction inside the NTDLL library. So as a result, for the EGR, it will appear more legitimate because we will be inside the NTDLL library. Then we have the PPID spoofing and the block DLL. So what we have to know is that for the EGR, Microsoft implements the update profile attribute Windows API function, which allow to add some mitigation policy for the process we create or the thread we create, which allows to specify some policy to deny some specific actions. So for example, here we are able to say, okay, I want to create a process, but for every modules you will load inside this process, I want them to be signed by Microsoft only. So in that case, if we have the EGR that have his own module that he will inject inside every new created process to be able to hook it. But in that case, if the EGR module is not signed by Microsoft, it will be simply not allowed to load his module inside our process. So as a result, the process will just not be hooked. So we can see the example here, just to create process. So my current process is hooked, but the new created process using the mitigation policy is not hooked anymore because the EGR was not able to load his module inside it because it's not signed by Microsoft. So another point to check for an EGR solution is that his module is signed by Microsoft to simply avoid this kind of bypass. So now a small demo. 20 minutes, okay. See. We'll try to post it here. Yeah. Okay. So here I have Cobalt Strike. I think everyone knows it. It's a C2. So I'm first executing a basic DLL just craft from Cobalt Strike without any change. You can see that the DR spot it and just block it. But then executing the same beacon, the same profile, but patching the ETW, patching IMSI, and using indirect syscall to perform the calls, then the DR is completely blind and we have the beacon connection. Let's go back to this slide. Oh. I lost the mouse. There it is. Then let's switch to the most important part. Racing Dodge. Okay.
Someone speaking Dutch.
Can I do full screen?
Speaking German or?
Wait. Start. Bottom right? Yeah. This one?
One more.
Okay. Thank you, dude. so we lost 10 minutes, okay. So now the most important part, or at least the most interesting, is kernel exploitation. So most of the time, kernel exploitation requires usage of vulnerable drivers, but it exists also some vulnerabilities which allows threat actor to access the kernel without drivers, but it's quite uncommon. So we have different type of drivers. We have, let's say, vulnerable drivers, but then we have also malicious drivers. So what we have to know is that for a driver to be able to be loaded inside the Windows system, it has to be signed by Microsoft. So there is some threat actors that can just succeed to sign their malicious driver by Microsoft and then load it to the system. Or we have vulnerable drivers which can be abused to execute specific actions, or then vulnerable drivers that can be abused to disable the DSC, the driver sending enforcement, which restrict the driver loading for signing Microsoft signed drivers only, and then be able to load any kind of driver we want, even unsigned. So we can see that the latest known exploitable drivers are these ones. In red, you can see that the actions they allow us to do. So depending on the drivers, they allow specific actions. But what you have to know also is that exploiting kernel stuff is quite dangerous because of patch guard and the kernel structure offset. So every driver's exploitation requires understanding of the kernel structure, and also must be exploited carefully to avoid the patch guard. Patch guard, for the guys that don't know, it's the security solution implemented by Microsoft to prevent kernel modification, which can lead to, at the worst case, the blue screen of death, or at the best case, the simply machine rebooting. So for example, if we take the example of the Gmer driver, it was the driver used to suspend thread of the EDR. So basically, drivers are mostly built the same way. So here we can see we have what we call the dispatch device control routine, which used what we call the input-output control code. So this input-output control codes are kind of like the interface that the driver creates to make the third-part application or user-land application to do specific calls to the driver. So basically, as a threat actor, we can abuse this kind of stuff, because if our input-output control code are not well secured, they can be simply abused. So this driver was used by threat actors to kill or suspend EDR processes. But now, as you can see, it's in French, sorry, but it cannot be abused anymore because the certificate has been revoked. So this is the best case, just simply revoke the driver certificate. But unfortunately, this kind of solution almost never happened. If you take the example of the Process Explorer driver, which is the Microsoft driver, it can be abused to do two different stuff. So first, it's to kill processes handles, or to open processes, protected processes handle. So this is the driver signed by Microsoft, and as far as I know, still now it can still be abused because it's not blocked. So, for example, if we look at the impact such vulnerable driver could have, so here we have an attempt to dump the LSAS process, which is protected with the run as PPL, which had the PPL protection to the LSAS process. So we see it's a fail. But if we use the Process Explorer driver to dump it, just succeed because we can abuse the driver to open a handle to a protected process. You can just see you lose some time. So you can see on the right, we have all the handles of the CrowdStrike process. And just executing the driver abuse, the Process Explorer driver abuse, we are able to simply kill It's still play.
Yes. Yes.
We are able to simply kill all the handle. As a result, the process is also killed. And then we can execute the dump of LSAS, which is normally blocked if the cross-write process was still running. We'll see just after. The process will restart. Then we'll try to re-execute our tool. Which is just blocked by the EDR. So we can simply just bypass it, just using the vulnerable driver. Then I was looking for a driver which performs some, which will allow kernel access. So I was inspecting different type of drivers, hoping to find some kernel read-write vulnerabilities, until I saw a tweet from a Windows kernel guy on Twitter that was just alerting on the Minecraft anti-cheat driver by Echo AC, which permits kernel read-write access. He did a POC, proof of concept, for local privilege escalation. So if we look at the driver source code, we can see that it exposes input-output control code, which perform copy virtual memory, and we control every parameters of this function. So basically, we can then abuse it using the eProcess kernel structure. As I said before, the kernel structure is very important. So if we want to local privilege escalation, we have to abuse, at least to have access to the xFastref structure, which contains the process token. Then the purpose is to read this token and then just copy it inside our own process. So basically here, we get the address of the eProcess structure. We read our own token. Then we can see here we get the token address of the WinLogon process, which is the system process. We get the system process token and just rewrite it in our own current running process. So as a result, we just go from simple user to anti-authority system. But for doing this kind of stuff, you have to be, of course, an administrator on the local system to be able to load the driver, unless the driver is already loaded inside the server, but has its anti-cheat for a video game driver. I hope any one of your server have already this driver loaded, because it can be kind of weird. But yeah. Then what we have to know also is that kernel rewrite vulnerability is like kind of a dream for every threat actors, because they can do pretty much everything they want, as you can see here. So I developed a tool to kind of perform any kind of stuff as a threat actor wants to do. So let's deep dive inside the ETW TI threat intelligence, which is kind of like the ETW from userland, but for kernel land. So as you can see here, compared to the simple ETW of the userland, in kernel land, it's directly executed after for example, the copy virtual memory. We have the call to ETW TI log VM, which is in kernel land, which means that from the userland, for the threat actor, it's impossible to patch unless you have access to a driver with, which allows kernel read-write vulnerability. As you can see here, it's allow as the ETW a bunch of logging providers. And then you have the kernel callback. That's what the EDR are using to perform hooking for our process. So kernel callback allows, it's the Windows mechanism that allow EDR to register to some specific callback. So we have the process callback, the thread callback, the load image callback, the OB register for the handles, and also for the registry. So basically the EDR will register to the callback they want, basically all. And then they will be notified by the kernel each time a specific action concerning the callback is performed. So for example, for the process callback, each time a process is created, the kernel will notify the EDR, then the EDR will hook this process. So basically, to patch the callback, we have to deep dive inside the kernel structure. We have some exported function inside the kernel. So for example, we can abuse or at least get the address of the ps setcreate process notify routine to get the address of this function. And then we will do some pattern searching for the call instruction, which will lead to the PSP setcreate process notify routine address, which contain the callback array, which store every driver that's subscribed to the kernel callback. So the goal is to abuse the driver to locate this callback array address, read it, and be able to write inside it. So basically, as I said before, we'll just get the address of the exported function of the kernel callback that interests us. Then search for the jump or call byte instruction, and so on. The read primitive function is the function that uses the driver to read or write. Then as a result, we can see that we are able to list all the drivers that register to the process creation callback. Then we can spot the EGR driver. So then we can just remove it. So we can see before removing the driver callback, the execution of Mimikatz is denied. But after the callback removing, the EGR just is not able anymore to see the creation of the Mimikatz process, then it's not able to block it. Or we can just remove also all callback, it works also. But then during real missions, it's better to restore the callback we just removed. Then for the ETWTI, we will work the same way. We will locate the function that interests us. So for example, here it's the goal of the ETWTI patching is to locate the address of the provider enable info. And to locate this address, we will get the exported kernel function ke insert qapc that use handle to the etw thread in progreg handle, which in fact is a pointer which lead to the etw guide entry structure. And this structure contains the provider enable info. So as same as before, we will do a kind of like byte pattern searching to locate the instruction that will lead to this handle to get the pointer to the etw guide entry, and then add the offset, which is 0x60, to get the address of the provider enable info. So as a result, you can see before the ETWTI is enabled. Then we do the pattern searching and just write 0 inside this address to just disable ETWTI. Then you have the process tampering. As we said before, the xfastRef token contains the token. But inside this structure, we have also the sep token privilege structure, which contains all the privileges of the process. So we have different fields. We have the present, enabled, and enabled by default field. Enabled by default, we just don't care, in fact. The two fields which interest us is the present and the enable. What we have to know is that if we try to enable a privilege that is not inside the present field, it would simply not work. What is the present field? For example, when we do the UMI/priv, we have 5 privileges. So all the privileges you don't see there, it's because it's not inside the present field. Otherwise, you will see them like enable or disable, but you will see them. So basically, we can do a lot of stuff just playing with privileges, enable, disable for my own current process. But hey, we can also do it for the other process. For example, the EDR process. So what happens if you try to do it for the EDR process? So we have access to the kernel. We can write pretty much everything we want. So we can just bypass the EDR without touching the kernel callback, but setting the integrity of the EDR process to untrusted instead of system. And then removing all the privileges that are inside the present field, so meaning that the process will not have any more privileges, and then be able to execute the LSAS dump without making the EDR completely blind. We can do also process tampering with the LSAS process. Just before we used the Process Explorer driver to dump the LSAS process, even if it was protected, because the driver allows us to open a handle to a protected process. But if we have access to the kernel as a read-write with read-write vulnerability, we can just remove any protection or add any protection to the process. So we can by ourselves just remove the protection of the LSAS process and then just dump it. But we can also add a protection, for example, our threat actor process. We execute our malware. We had the protection, for example, PPL protection. The EDR processes are running with the anti-malware protection. It's a level of privilege which is just under the PPL protection. So it means that the EDR will not be able to inspect or to scan our process, our malware process, which is running as a PPL process. So as I said before, the EDR process is running with slight anti-malware process. Even with administrator privileges, with normal EDR, we are not able to kill EDR process. But if we remove the protection anti-malware of the EDR process, we can just then kill it. Simple. So there is a lot of different ways we can have used with kernel read-write vulnerability to do a lot of stuff which could be interesting for threat actor. So, the time good. As a conclusion, so what a company should look at when we speak about EDR? As we saw before, must have AMSI support, module signed by Microsoft, and if possible, LAM drivers, so early launch anti-malware driver, to be able to make the EDR able to use ETW-TI instead of the ETW which run in Ireland. Regarding threat intelligence, EDR which performs threat code stack analysis to detect any kind of hook bypassing. There are strong malicious binary process detection capabilities, the string, entropy, memory scan, the behavior sandbox, kind of the basic. An active security researcher team, because it's important to keep updated, even for drivers, because for the latest exploited drivers we saw, like ZAM, Process Explorer, or GMAR, there was a lot of blog articles, even from media vendor, concerning these drivers. But what you can see in real life is that these drivers are still not blocked and can still be exploited by attackers. And EDR, XDR is not the only protection. Of course, we have app locker, proxy configuration, system, Active Directory hardening, network segregation, firewall, that are also important. And regarding IT administrator out there, Microsoft implements in 2022 the Windows Defender application control, which allows to create a driver blocklist to prevent the execution of known vulnerable drivers.
Yeah, the key point about this talk to conclude is for the red teamer to present our approach, how we bypass the solution, what you can do, how you can implement this kind of stuff, and for defender to know what happened in real life, because you can defend only what you know. Thank you.